So for our project, we decided to study the impact of different characteristics on an athlete's weightlifting performance. So for the background of our study, this is a confirmatory observational study, and it aims to determine how a variety of characteristics affect weightlifting performance. So weightlifting can provide numerous health benefits, and in our case, we are looking at competition-style weightlifting. Characteristics like age, gender, body weight can impact the amount of weight that an athlete can lift. Past studies have shown the difference in weightlifting across age, gender, body weight groups, and we would like to further confirm these studies. So when we did a literary review to see how our study is relevant to other studies, we found similar research by Christopher Latella and Nathan Petitfus. And so Latella and his team at Edith Cowan University displayed that impacts such as age, gender, and body weight have a significant impact on strength and the amount of weight that someone can lift in competition. And then Nathan and his team showed us an ideal ratio for maximum weightlifting.
Research question 1. Does equipment have significant linear impact on a competitor's performance while considering age and body weight? Many metrics for performance are available to us, ranging from weight lifted for an individual lift all the way to industry-specific KPIs. Total weight incorporates weights lifted from different individual lifts. Total weight is also how some competitions place their participants. It should be a good metric for performance. Age denotes the age of a given competitor at a competition. We believe the interaction of equipment and age is important. By including age, we can better understand how equipment impacts performance. Body weight denotes the body weight in kilograms of a given athlete. We also believe the interaction between body weight and equipment is important as well. And we also believe the third order term, the interaction between age, body weight, and equipment, is also important. Similar to age, including body weight can help us better understand how equipment impacts performance. Equipment denotes if an athlete used equipment to aid in their lift and what kind of equipment they used. Note that equipment has been reduced from multi-level qualitative variable to a binary indicator variable to better reflect our study and our purposes. We performed some diagnostic checks. Based on the red line, we see that our residuals are not exactly centered at 0 and appears that they follow some sort of downward trend. This indicates that there may be a linearity violation. We observe the residuals do not have an even spread around the red line. This indicates we have a heteroscedasticity issue. This is supported by a low p-value from the BP test. We see that our residuals do not follow the QQ plot well at the left-hand tail. This indicates that there may be a normality violation, and this concern is supported by a low p-value from the Shapiro test. The large VIF values that are greater than 10 are produced for each predictor variable. With our cutoffs and plots, we see that outliers and influential points are present in our data. Many different types of models were tested to address these issues, and this combination performed best, mean centering and standardizing X values, and by performing weighted least squares. The linearity issue was not improved by this solution, or at least not significantly improved. The non-constant variance issue was improved. We can see this as the residuals now have a more even spread around the red line, and the Bruch-Pagan test, the BP test, has a higher p-value. Our QQ plot indicates that the normality issue has been corrected, but the Shapiro test contradicts this. We're going to go with our conclusion from the QQ plot. We also see lower VIF values, all less than 10 for all of our predictor variable terms. As for our cutoffs and outliers and influential points, we see a general decrease in all of them except for DF betas. In DF betas, we see an increase. This is notable since we're trying to perform a GLT test with our research question. GLT test concerns beta values. DF beta says that there's influence on our beta values. So we're going to keep this in the back of our head, but overall look at the big picture that there's a decrease in all of our outlier influential point metrics, apart from DF betas. As a quick recap, we had a linearity violation that's been improved but still present. There's been a non-constant variance issue which has been corrected, a non-normality issue which has been corrected according to the QQ plot. We had a multicollinearity issue that's been corrected. The presence of outliers and influential points, they're still present, but it's overall been improved. As for our research question, we're going to be performing a GLT test. We observe that we get a low p-value. This causes us to reject our null hypothesis and believe in the alternative, which answers our research question. Does equipment have significant linear impact on a competitor's performance while considering age and body weight? According to our GLT test, the answer is yes.
This research question is testing the same y using a different x. So the first part is, does the lifter's age have a different impact on the total weight they can lift when their gender is female versus male? And that is tested using a GLT test. However, the second part is then testing that interaction to see if it fits the model using a lack of fit test. So again, we are still using age, but now we're using a new x variable, gender. It is categorical, so what we have to do is change it to be zeros and ones. We are testing the interaction also, x1, x2, and then finally using the same y. So first we need to test the assumption linearity, and we do see there is a violation, as from the scatter plots it is not linear. We then look at the variance diagnostics, and we see that yes, it is not linear, and there is possible non-constant variance based on the BP test, which we use since it is an MLR model. Finally, we test the last assumption, normality, and we do see that it is not normal based on both the histogram and the Shapiro test. So we have to transform the y using Box-Cox to fix this normality and variance issue. So then testing for multicollinearity now, we do see that we don't have an issue with that, but there is an issue with x outliers. So we have to remove those x outliers to make sure our data is okay, and once we do that, we do see it is now, for the most part, normal based on the histogram, but not the Shapiro test. So we are also going to be testing for influential points, and we can see here that there are not any influential points. So we can keep moving on to now finally testing our question. We conducted OLS, but a WLS needed to be conducted because of the unequal variance, where bootstrapping remedies were conducted on top of that because of the non-normality issues. And then for our research question, we actually did end up finding the answer that the interaction between age and gender did impact how much a lifter can weigh. So that's something they should start considering when they are doing their competitions. And then for the second part of the research question, we did see that the interaction did fit the data. So there is a relationship between these predictors and the y variable. And finally, the cross-validation did confirm that there was a high predictability and a very low RMSE score.
So for my research question, I was wondering about the effect of gender being either male or female, and if it has a significant linear impact given that age and body weight are already included in the model. I chose gender and age for predictors in the model because gender is a categorical variable with two levels, male or female, and age is a continuous variable, and I think that both would have an impact on the total kilograms an athlete can lift. I also chose body weight as a predictor of total kilograms, which is the sum of the best squat, best bench, and best deadlift per athlete. So for this slide, I just showed my models and the summary, and the reduced model does not include gender, the full model does. And from the ANOVA tables, we can see that we should reject it all and conclude that gender does have a significant linear impact given age and body weight are already included in the model. So we should include gender in our model. So when I was doing model diagnostics for my first model, I chose to test linearity, normality, constant variance, and multicollinearity. So we had violations on normality and constant variance, but linearity and multicollinearity looked fine. Some more diagnostics include outliers on Y, which we didn't find. Outliers on X, we found a lot. We found some influence on regression coefficients, and we did not find any influence on all fitted values, but we did find some on single fitted values. I also chose to transform Y with Box-Cox transformation based on our violation of normality and our violation of constant variance, and I had to add a constant to each of the data points before due to the negative values due to normalization, and I also removed outliers in the hat matrix. After transformations, we see some improvements in our diagnostics, but we still have a normality assumption violated and constant variance assumption violated, and this time we have a multicollinearity assumption violated as well. Further, all of our assumptions that were previously violated are also violated after the transformation, but our plots look a lot better. Since our transformation did not take care of all assumptions, I also tried weighted least squares for unequal variances, robust regression for outliers, and I also did bootstrapping to show the confidence intervals below. Finally, I did k-fold cross-validation over 10 folds and concluded that the RMSE is 0.382, and this RMSE is pretty low, so the predictions are good.
Moving on to the next research question, I wanted to see if where weightlifters' weight fell within their weight class was significant. So I decided to explore the question, is the difference between a lifter's weight and the maximum weight of their weight class a significant predictor for IPF points, given gender and age are already included in the model? Like the last research question, I'll be including sex, a categorical variable, and age, a continuous variable. Uniquely, though, one of my variables is weight class minus body weight, to get an idea of how close to the maximum weight a lifter is in their class. And also IPF points, a point system that balances scores so men of any weight and women of any weight can have comparable scores. Now to check assumptions. Based on the Shapiro test and the QQ plot, there exists a normality violation. Based on residual plots and Bruce-Pagan test, there is a heteroscedasticity or constant variances violation. Based on AV plots, age may not have additional information beyond what's contained in the other variables, and based on VIF, there are no multicollinearity violations. So we ran into a few problems, including constant variance and normality. So that's why we're going to transform Y, which I did with Box-Cox, in a lambda of about 0.88. However, when going back through and looking at our assumptions, normality, heteroscedasticity, linearity, and multicollinearity, we don't improve. The assumptions we were violating before are still being violated. So we'll now instead try a WLS to resolve our issues. But normality, heteroscedasticity, linearity, and multicollinearity, again, we don't improve. The assumptions we were violating before are still being violated. Looking at outliers, right offhand it looks like we have none based on our hat matrix for X outliers and our studentized deleted residuals for Y outliers. But we also need to look at DF betas and Cook's test. DF betas identifies about 70,000 candidates for influential points, but Cook's distance tells us that there are no influential points that affect the overall fitted value. So now we look at multiple models for bootstrapping, including WLS, which we've looked at before, which can help with unequal variances, and robust, which could help with outliers. Moving past our faulty data, our conclusion is that the difference between a lifter's weight and maximum weight of their weight class does have a significant impact on the lifter's IPF point score, given gender and age. But based on k-fold cross-validation, it should be noted we do not have strong predicting power, and this conclusion could be unreliable.
So for research question 5, I wanted to investigate the effects on the specific exercises completed in a competition. Formally, the question asked if a lifter's best squat and best bench press have an equivalent linear impact for determining their place in a competition. The null hypothesis is whether beta 1 equals beta 2, and the alternative hypothesis is whether they do not equal each other. Here is an explanation and some information on the variables used, where place represents what place a lifter comes in, and the best squat represents the heaviest squat weight a lifter lifted. Best bench press and best deadlift also represent a lifter's heaviest weight successfully lifted in each respective exercise. All three of these exercise variables have been normalized for our convenience. As we can see, because of the low p-value, we reject the null hypothesis. There's enough evidence to conclude the linear impact of a lifter's best squat is different than that of their best bench press. Taking a look at the initial diagnostics, the model has quite a few violations on linearity, normality, and constant variance. Because of this, a transformation on Y is necessary. A lambda value of negative 0.5 is used in the Box-Cox transformation method here. The result remains consistent. The null hypothesis is still rejected. There is still enough evidence to conclude the linear impact of a lifter's best squat is different than that of their best bench press. Taking another look at the diagnostics reveals an improvement in almost everything. However, there is still a slight violation on constant variance. Furthermore, looking at some more diagnostics shows a bunch of potential influential points from the influence plot and DF betas plot. yet none of these are actually confirmed in the Cook's distance plot. Additionally, here are the bootstrapped confidence intervals for a few different methods, all with similar results for the exercise's impacts. Notably, WLS is used to help improve the unequal error variances, and robust regression is used to help with the outliers. Lastly, the K-folds cross-validation method was conducted on this research question, showing a high prediction power with a very low average RMSE value.
Overall, our research questions had significant results with strong predictive power. They also contributed to past research by using unique combinations and interactions of predictors that weightlifters can use to help improve their total points, their place, and the total weight. All the questions were based off of prior research and common sense. However, they did have a unique twist of using interactions and unique combinations. One of the many pros is that we got to apply what we learned in class to real-life data, but because it was real-life data, there were a lot of concerns with diagnostic issues and quantitative variables were lacking. So next time we would pick a better data set and get to explore more about the differences and impacts.
Here you can find our references, and thank you for watching.